This short video is going to deal with the topic of nomenclature, and specifically it's going to deal with the naming of simple binary ionic compounds. So first of all, it's useful to have an appreciation for what nomenclature really is. So let's have a look at this definition, and you'll see a lot of weird stuff that comes out of a dictionary, but also 2, the act or process or an instance of naming, and 3, a system or set of terms or symbols, especially in a particular science, discipline, or art. And so what's that particular science? Well, really, for you, this is chemistry. And so we are going to name chemical compounds based on a formula, and we're going to write the formula based on the name, and that is really the nature of nomenclature. So let's get started. One of the first things you have to be able to do is get the correct common charge for the elements you're looking at. And so for us, that's really quite straightforward if we single in on these Roman numerals. And so the Roman numerals, 1A, 2A, 3A, etc., up to 8A, give us the number of valence electrons. So Roman numeral equates to number of valence electrons. Now you'll notice I don't have the entire periodic table here on the screen. I have the long columns. So on the extreme left we have 2 long columns. That's the alkali metals and the alkaline earth metals. And on the right hand side of the periodic table we have slightly shorter columns, but still long columns leading up to the halogens and noble gases. What we're missing is the big D block. And so these are known as the representative elements or main group elements, and we can use the Roman numeral system to determine the number of valence electrons. So it's really only used for the main group or representative elements. There's another way we have to deal with things in the transition block, in the D block. Okay? But using this, we can quite quickly determine number of valence electrons. If group 1, for example, with 1 valence electron is going to form an ion, it's going to lose a single electron and become a cation, a sodium plus ion, for example. If we go to the other side, something like oxygen in group 6 has 6 valence electrons. It's not going to lose 6. That would require too much energy. Something on the right-hand side, the nonmetals will gain electrons, so oxygen with a 6 will gain 2 to form a stable octet and become stable. So oxygen becomes the oxide ion O2-. So that's how you use the Roman numerals, number of valence electrons, and then determine how many electrons need to be lost or gained. Metals will always lose, form cations. Nonmetals will always gain and form anions. So we're going to deal with ionic compounds only in this short video. So an ionic compound can be defined basically or described as a metal combining with a nonmetal, and we're talking about binary, so that's really only individual atoms of the metal nonmetal type. Name follows a simple pattern. The metal is listed first, the nonmetal is listed second, but we change the ending, the nonmetal, from something like chlorine to ide, chloride. The formula for a neutral ionic compound is arrived at by putting together the ions, the common ions that are formed, such they obey the zero-sum rule, and I'll explain that in just a second. Okay, so that's what we need to do. So we're going to put together a compound formed from sodium and chlorine as an example. So sodium and chlorine. So they're the atoms. So the first thing we have to do is decide number of valence electrons. So sodium is in group 1, single valence electron. It's going to lose 1 and become an Na plus ion. If we go over here, we have chlorine as a nonmetal on the right-hand side of the periodic table, a halogen in group 7, 7 valence electrons. It's going to gain a single electron and become a chloride ion, Cl minus. So we have Na plus and Cl minus, and they're going to form an ionic compound. And so we put them together, and there they are, and we have to determine whether that obeys the zero-sum rule, because the zero-sum rule is going to indicate how many of each we need. So zero-sum rule essentially says the sum of the charges is 0. And so when we sum up these charges, we have a positive charge. We're going to add it to a negative charge. So a positive plus a negative equals 0. So that obeys the zero-sum rule. So that is in fact the formula for Na, or for sodium chloride, NaCl. And so again, the name, sodium, the nonmetal first, the metal changing the ending to IDE, sodium chloride. Okay, so that is how you name an ionic compound. Let's just look at a couple more examples. So magnesium and oxygen. So again, we need to go to the periodic table to quickly determine charge. And so magnesium and oxygen, well, here's magnesium in group 2. It will form a 2+ cation. Here's oxygen in group 6. It's going to form a 2- anion. And so if we put those together as Mg2+ and oxide 2-, we get a formula MgO, and that obeys the zero-sum rule. 2+ plus 2- equals 0. So that's the formula for magnesium oxide. So again, name magnesium oxide. Oxygen, change the ending to -ide. How about calcium and phosphorus? Well, again, let's quickly look at the periodic table and get our charges. So here's calcium, again, group 2, so it's a 2+ cation. Here's phosphorus, group 5, so it's going to form a 3- anion. It's going to gain 1, 2, 3 electrons. So phosphorus is 3-. So Ca2+ plus P3-. We put that together, CaP. Now if we left it at that, we would have to check zero-sum rule. 2+ plus 3- does not equal 0. It in fact equals -1. So we have to balance the charge by adding more or less of the individual ions. And so the simple way to look at that is something known as the crisscross rule. And the crisscross rule says take the magnitude of the charge, that's a 3 for phosphorus, and make it a subscript for the opposing or other element. Take the 2, make it a subscript for the phosphorus. And so if we write those in, we have Ca3P2, and let's look at the zero-sum rule now. So 3 times 2+ is what we're looking at there, and we're going to add that to 2 times 3-, and that does in fact equal 0. 6+ plus 6- equals 0. So this formula, Ca3P2, obeys the zero-sum rule, and that is the formula for calcium phosphide. And so that is how you deal with naming simple binary ionic compounds.